So now that we have our unit circle and we've been looking at evaluating sine and cosine off of it, let's talk about some extensions of the use of the unit circle. And again, we're just going to focus on sine and cosine here. In the next set of videos, we'll bring in those other trig functions. So first thing is this idea of symmetry that's all across the unit circle, which we talked about when finding all of those different coordinates. The idea is that no matter where you are, there are these points that can be reflected across the y-axis. So those would have the same y coordinates. Across the x-axis, those would have the same x coordinates. So what we can see is that for these outputs of cosine and sine, which are x coordinates and y coordinates, actually have two locations where we can see like the same y value in two spots for two different angles. So let's evaluate that with this example here. So if cosine of t, which again, cosine is relating to our x coordinate. So if that x coordinate is equal to 2/9, and t is in the fourth quadrant, what's our value for sine? So having an x coordinate of 2/9, and if it helps, what you could do is take 2/9 and get a decimal approximation, which is about 0.22. So the idea is on our x-axis here, right here is 1. So 0.22 is maybe about, let's say here. So if that's our x-coordinate, there are these two locations on our unit circle. There's this location that's in our first quadrant, and then there's this location in the fourth quadrant. And that's what they're specifying here, is that since our angle t is in the fourth quadrant, this is the value we're looking at. So what we have here is this terminal side that's landing at this angle t. So t is actually going all the way around and then lands there. There's our angle t. And at that coordinate, what we have is we know our x coordinate is 2/9. What we don't know is what the y coordinate is. So when they're saying find sine, really it's saying find the y coordinate. So this value t, this value of 2/9, this isn't one of those special values that's showing up on our unit circle. So we need to do a little bit of work here. So something we're going to use is the fact that we have this x coordinate. And in fact, I'm just going to recreate this triangle that we're seeing here, just a bit bigger. Sorry, I'm going to make that a little more clearly a right triangle. Yeah. Okay, there's our right triangle. And what we know is that this distance along the x-axis, that's our 2/9. What we also know is the radius. Because we're on our unit circle, this radius right here is 1. So what we have here are two side lengths to our right triangle, which means we can use the Pythagorean theorem. So we've done some practice of solving for side lengths using our trig functions, but that gets tricky here because we don't actually know our angle measurements. We have an idea of our angle measurements in terms of us landing in the fourth quadrant, but other than that, we don't know the specific value. So with that, we want to solve for this side length, which will give us our y coordinate, which is our value for sine. So Pythagorean theorem, we have one is our hypotenuse, and then the other two side lengths are the legs. So we're going to have 2/9 squared plus y squared equals 1 squared. Now 2/9 squared is 4/81. I'm going to keep these in exact values. I'll show you how to have the calculator help you out. Equals 1 squared is 1. And then we're going to subtract 4/81 from both sides. So y squared is going to come down to, and for 1, we could represent that as 81/81, and subtracting away 4/81. So y squared is going to be equal to, that should be a 77 in the numerator, over 81. And then we would take the square root of both sides. So for an exact value, y is the square root of 77 over the square root of 81, which is equal to 9. Now, with fractions, if you're a little rusty with them, that's completely fine. What you could do is do 1 minus 4 over 81 in here, and it'll give you the decimal form, but you can convert it to a fraction, so you can see your reduced fraction form there to help out. All right, so we got our y coordinate, but again, this is all about finding sine, so just be sure to take that extra step to say sine of that angle t is equal to the square root of 77 over 9. So there can be these questions where they give you sine or cosine equal to a value, and it's essentially giving you the x or y coordinate, and then using the placement of the angle, you can find the other coordinate with the Pythagorean theorem. All right, let's see what happens if we change the radius of the circle. So if we're working with an angle measurement where we know sine and cosine, but sine and cosine land on the unit circle, so a radius of 1. So what happens if we want to find coordinates on a circle that has a larger radius? So what we'll have here is, let's say we have our circle, and I'm going to have this be my circle that has a radius of 20. So with this, we're going to call that 20. We're going to be at 120 degrees, which is 90 degrees plus 30 degrees. So we are here. So here we have this angle of 120 degrees, and we want to find this coordinate. Now, the idea here is that our unit circle is completely embedded in here. So I need to write that 120 a little smaller so I can fit it in here. This might not be perfect, but as best I can. Ooh, sure. Imagine that's a nice little perfect unit circle in there. The idea being, we know the coordinates on this unit circle. We know sine and cosine there because that would be, x would be our short side, which would be negative, so negative 1/2. Y would be the long side, which is the root 3 over 2. What we can notice though is that they're really relating to the same triangle. It's this 30, 60, 90 triangle coming through. So let me just bring that to the side here. And what I'm going to do is put this in kind of more abstract terms of just sine and cosine so that we can relate this to any radius that we deal with. So the idea being, with our smaller triangle here, that would have values of a radius of 1. Along the height there, that would be our sine value, since that would be y. And then cosine would be along the bottom, right there. So that's our unit circle triangle coming through. But then what if we extend it? What if we want to look at this hypotenuse that's actually equal to this new radius? And then we would have some y coordinate and some x coordinate. And what ends up happening is we can use similar triangles here. So the idea that there's this scaling happening. We're scaling 1 up to a scale of r. We're scaling sine theta up to y, and we're scaling cosine theta up to x. So there ends up being this proportion relationship. So let's say I related this as x and its scale to cosine theta should be equal to taking that new radius r equal to the radius of our unit circle, which is 1. And if I solve for x here, what ends up happening is the x coordinate is just coming from taking this new radius that we're dealing with times our cosine theta value. And the same exact thing happens with y. If we think of y scaled to sine theta should be equivalent to r scaled to 1, solving for y should be the same as r times sine theta. So this is a rule that we're going to use here. We just hadn't derived that rule before, but it comes from the idea of similar triangles, but we can use this. So what we're using in this example here is the fact that we have an angle measurement of 120 degrees. We have a radius of 20. And what we also have is, we know these values, cosine of 120 degrees. So our x-coordinate is -1/2 on the unit circle. And sine of 120 degrees is that √3/2 for our y-coordinate. So using those pieces together, what we can do is find the x and y coordinate on this radius of 20 circle by finding our x-coordinate, taking 20 times cosine of 120 degrees, which is 20 times a -1/2. So just making that substitution of cosine of 120 degrees is exactly equal to this -1/2. So putting that in there, so we're seeing an x-coordinate of -10, and our y-coordinate, it's the same process, just with sine. So we're taking 20 times √3/2, which would be 10 times √3. And what I do is a quick little mental check that the signs make sense, meaning we are having a negative x-coordinate, positive y-coordinate, because 120 degrees lands in the second quadrant. So that's our coordinate. We would have the coordinate -10, 10√3. So that's what we can do when we extend the radius. You don't need to do all these steps of deriving. When you solve these, you can just use this property that when we work with a different scaled radius, x equals r times cosine of theta, y equals r times sine of theta. And then you can just jump to the calculations. All right. So what if we want to take cosine and sine of values that are not the special values showing up on our unit circle that we filled out? Because the idea being, if I just jump back to our unit circle for a moment, where we label these coordinates, there are infinitely more coordinates in here. Like we can take the cosine of 10 degrees, 20 degrees, 70 degrees, any measurement, any angle measurement within 0 to 360, even beyond, because we're just using reference angles really in the evaluation of it. We can land absolutely anywhere in here. Now the set has restrictions to it, and that it has to work within this set. Like if we're on our, sorry to go back even further, like if we're on our grid here, getting sine and cosine values, I'm not going to get a solution of what, negative 1.5, 1.5. That coordinate is not possible. So we do have restrictions on the coordinates that can come through, but the idea is that these coordinates that are along the outside, there are infinitely many of them because we have infinitely many angles going in between there. So with that, we can find many other values. They just don't have nice properties with special triangles. So with that, we rely on our calculator. Now, when we go to our calculator, be sure to make note of if we're in degree mode versus radian mode, because that will give two different answers, meaning having like 10 degrees is very different than having 10 radians. So first thing we want to do is make note of the angle that's inside and whether it's degree or radians. In this case, it's radians. So what I want to do is just go to the calculator and we're going to go cosine of, and I'm in degree mode here, so I'm going to switch over to radian mode, and we're going to have 5 pi over 9. Oh, I layered my fractions. Okay, there we go. And it's a negative 0.1736. I'm going to go to 4 decimal places there. So negative 0.1736. And that's it. To check your answer, you could kind of visualize where 5 pi over 9 is landing in our unit circle. This gets a little tricky, but the idea should be that when you check it, the x-coordinate's negative, so it should either be up there or down there. Sine of 310 degrees. It's a little easier for me to visualize. Again, radians are kind of new for us. 5 pi over 9. Well, let's see. 5 over 9. Let's do this. 5 over 9 is about 0.5. So I'm going to think this is fairly close to a half of pi. So I'm going to make a note of this. 5 pi over 9 is pretty close to pi over 2, which means, and it's just a little bit larger because it's like a 0.56. So that makes me think we're landing there. And with that, I can see that would be a spot that would have this kind of small negative x coordinate. So that makes sense. Sine of 310 degrees, well, that's about 40 degrees larger than 270. So I'm thinking we're about here-ish. And we're getting the y coordinate. So I'm going to expect a negative value out of this. Let's go to our calculator. I need to switch over to degree mode. And then we're taking sine of 310. And that's a negative 0.760. 0.766. So that makes sense because sine is our y coordinate. So we should be having a negative value. Also, like if I drew this in more detail, that makes sense that it's pretty large. It's getting pretty close to -1 since we're kind of close to that 45 angle with the root 2 over 2. And here it makes sense that it's so small because we expect to be pretty close to that pi over 2, which is at, for the x coordinate, close to 0. So I just want to give that as an idea of like, how do you know if you're even on the right track with these? And it's a way to double check that you're in the correct mode, because if you switch to radian mode, you see how those changed when I switched over, and you get a positive number. So having that kind of instinct with it can help check your answers. All right, the last piece I want to go over here is domain and range for sine and cosine. So let's look at sine theta and cosine theta and describing the domain and range for each. So domain and range, it's our possible inputs and possible outputs. So domain is all about what are possible values that we can input, and range is about possible outputs. So domain of our sine function. So I want to know what's our possible inputs, and the input for our function is the angle measurement. Now, what you might think is that, okay, we're restricted from 0 degrees to 360 degrees. That covers all the angle measurements. And that's almost true. But the idea is that we could keep rotating. We could go beyond 360 degrees or beyond 2 pi. We could keep doing revolutions. The idea is that we would end up at a terminal side and then we could graph it and then find the coordinate. So, and the same goes for negative, in that we could go in the opposite direction. So we can have a negative angle measurement as an input. So, and it doesn't really matter degrees or radians here. It's just that we could have these infinitely many positive and negative, or even 0. We can have an angle measurement of 0. So our domain is all real numbers. And the same goes for cosine. In terms of inputting an angle measurement, we can input all real numbers. So our domain, no restriction. Now for range, thinking about our possible outputs. So for sine, the output of this function, we're going to think of it as our possible y coordinates on our unit circle. So if we're here, we can think of our possible y coordinates as we go around the circle. So what happens here is I have a y coordinate of 0, it gets a little bigger, 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 and then it hits a maximum of 1. But really, we could have any value between 0 and 1, and including 1 and 0 as well. So inclusively, we could be at 1 or have anything until we get to 0. And then continuing on, so over here we just have kind of repeats of those same values. And then we have negative values, and they get smaller and smaller and smaller and smaller until they hit -1. So then we can have any values going down to here and including -1. But what we aren't going to see are y-coordinates that go above +1 or below -1. So our range for the sine function is we're restricted between -1 and +1 inclusively, including those endpoints. So our range, use the square bracket, so we include that -1, go to +1, including that endpoint. So we can have any values between and including -1 and +1. Now for cosine, pretty much the same thing happens, except we're just looking at our x-coordinate. So for our x-coordinates, we can have 0 as a possible x-coordinate coming through at those points. And then we can see we have these positive x-coordinates, positive, 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 until we get to +1. So we're seeing all of these values up to and including +1. And same thing on the other side. We have these negative values. So for cosine, we're going to have values between -1 and +1 as well. All right. So those are some extensions of our unit circle, the domain and range, using our calculator, changing the radius, as well as using symmetry.